The rate of a chemical reaction depends on the frequency and effectiveness of collisions between particles. For gases, compressing the volume increases pressure. The same number of molecules are confined to a smaller space, so collisions occur more often, increasing the reaction rate. For solids, only particles at the surface can react. Grinding a solid into a powder increases surface area, exposing more reactive sites and raising the rate. In solutions or gases, higher concentration means more reactant particles per unit volume. With more particles present, collisions are more frequent and reactions proceed faster. Increasing temperature has two effects. It increases molecular speed, which produces more collisions per unit time, and it alters the distribution of molecular energies. According to the Maxwell-Boltzmann distribution, not all molecules in a sample have the same kinetic energy. At lower temperatures, most molecules cluster around a lower average energy, and only a small fraction exceed the activation energy barrier. When temperature rises, the distribution curve shifts to a higher average energy, and it also broadens. We can think of activation energy as a hill that reactants must climb in order to transform into products. Some particles have enough energy to make it over the hill, but many do not. A catalyst works by lowering the height of this hill. This reduces the activation energy required. It is easier to climb a shorter hill than a taller one, but not every collision forms products. For a collision to be effective, molecules must have energy greater than or equal to the activation energy, and the molecules have to collide with a correct orientation. For example, let's look at the gas phase reaction of nitric oxide with ozone to form nitrogen dioxide and oxygen. If the molecules strike in the wrong orientation, the collision fails, even with sufficient energy. But with proper alignment and energy, the collision results in the successful formation of nitrogen dioxide and oxygen.